Okay, I think we can start if you're ready. Yes. Okay. Good afternoon, everyone. I'm very glad to welcome you all at Kyiv Academic University. Today we start the HPC workshop. The lecturer will be Jiří Vyskočil, who comes from Casus HCDA. He'll tell more about the organization and about himself as well. Just a few short words about Jiří. This is the second time Jiří comes to Ukraine. Last time he came in May, when actually was this first huge attack with Kinjals, with 6 Kinjals, and it was very brave of Jiří to come here and like with this great mission of like teaching and supporting science in Ukraine and supporting Ukraine in general. His past experience, specifically in HPC, mostly involves plasma physics and calculations on supercomputers with many nodes and many CPUs. So during this workshop, you'll learn some basics of parallel programming in C, C++, and then also we'll be able to calculate some simple stuff on the cluster of Bogoliubov Institute of Theoretical Physics. So Jiří, please. Word to you. Thank you very much for coming.
Thank you. I'm glad I'm here again. As Volodya said, it's my second time, and the last year when I was here in May, I wasn't teaching an HPC workshop. I was here with a different project, which I also repeated this year. That was the scientific visualization and multimedia art in virtual reality. Because scientific visualization is something that I used a lot together with doing those plasma physics simulations on clusters, because from those large simulations you get a lot of data and you need some meaningful way how to understand the data, how to see what's actually happening there. And through that I also got into making multimedia art exhibitions with virtual reality, basically using the same technology or very similar technology to the one I'm using for the visualizations. But yes, today we are here because of the HPC workshop. So my experience with that, I basically did my PhD on plasma simulations on large clusters. I finished in 2019, and back then the biggest simulation I ran used something about 40 or 50,000 of CPUs, and single run generated something about 100 gigabytes of data. And I did like some parameter scans over several simulations. So at the end, when I was writing my thesis, I needed to sift through about 2.5 terabytes of data and somehow make sense out of that. And I will not touch data analysis here much, because that's also like, I would say, a topic for another full workshop. But I will touch the part of the simulations themselves. So we will talk about clusters in general. What's the difference between a cluster and your usual laptop or desktop computer, and then how to program how to create parallel programs, how to write parallel programs running on a single computer but with multiple cores, because nowadays basically every laptop has many cores, even the mobile phones have many cores. And then how on a cluster run simulations that run on different nodes, which are like separate computers basically connected through some network. And there are different technologies for that. I will show the most common ones, OpenMP and MPI. I will also briefly talk about GPUs, but we don't have a GPU cluster, so we will not try that. The workshop will, like every day, it will have two parts. We start with some theory, a presentation, and then that will be the first half, and the second half will be some hands-on workshop and where you will actually try the stuff I talk about on the cluster. And for the first 3 days, so today I will talk about clusters themselves, how they operate. Again, what's the difference between the cluster and let's say laptop. And in the second half, we will connect to the cluster and run some basic jobs, interactive jobs, look around the cluster, see how it works and how to operate it. Then tomorrow, okay, I kind of, yes. Tomorrow I will talk about parallel algorithms. So it will be more about programming. What are the analogs of the usual algorithms? For example, what's the analog of a for loop in a parallel setting? Because that's how do you make the program parallel? That will be the question for tomorrow. And for the hands-on session, we will not immediately apply that because we will continue with what we start today, and that will be basically writing job scripts using the scheduler on the HPC cluster, because that's one of the differences between normal computer and the HPC cluster. Usually on the HPC cluster, you need to schedule your job because there are many users and everyone wants to run their stuff there. So this has to be somehow solved by the infrastructure on the cluster. On the third day, we will do some parallel programming actually. So basically the theory from the second day will be applied on the third day. I will show you what's MPI, what's OpenMP, and we will write some basic programs in that. And for the fourth day, I called it Practical HPC Applications and Conclusion. And basically, during those 3 days, we can also talk about your specific requirements or like projects you are working on projects you would like to work on, and we can make it somehow more individual and look into some specific topics a little bit deeper, based on what the people here would want to hear and see. Okay. I think that's about me and the overall structure of the workshop. And now I would like to ask you to briefly introduce yourselves and tell me what's your previous experience with clusters, if you have any, if you have ever done something on a cluster. What's your experience with, and if not, or even if yes, then what's your experience with Linux? Because the clusters, all the top 500 clusters nowadays run on Linux, so you will need that. If you don't have any experience with those, don't worry, because the workshop is actually structured so that you will learn the basics that you need. But that also means that if you do have experience with Linux and the clusters, maybe the first day hands-on session will be a bit boring to you because you've probably seen most of it before. So,
Hello, everyone.
My name is Jiří, and I'm a final year fellow student at HPC, and I have no previous experience with clusters, but I'm interested in to look how it works and gain some basic understandings about.
Okay, and with Linux, have you worked with Linux before? No. Okay.
So hello everyone, my name is Nicola. I'm currently a first-year master at KAU at Computer Science. Previously, I've studied at KPI system analysis. It was like a combination of rigorous mathematics and its application in machine learning and data science in general. So currently, I'm like moving towards like applied mathematics stuff with those like ML applications and stuff in statistics and just numerical optimization. So about Linux, I've had like one course at my bachelor's, but it was like some basic stuff with folder manipulation files, etc. So just some basic stuff, and never used it as my main software here. And about clusters, no, parallel computing is completely new to me, so I'm just absolutely excited to learn more because I believe it will be crucial for any further endeavors.
Okay, good. About what we learn from Linux, it will be those basics, like how to move files around and like how to see what's in the folder and stuff. We won't need like much, just those basics, but then specific stuff for the cluster, how to actually run software on a cluster.
Cool.
Yeah.
Okay, my name is Carla. I'm second year. Here. Master student at Jiří University. I have some experience with this specific cluster. I ran my calculation from institute for there. So some limited experience, with Linux, like basic stuff. Right?
Okay, so you can actually help me in the afternoon.
We'll see. This cluster has some strange behaviors. You can say so.
Okay. Yes, my name is Alexei. I'm also a first-year master student at KAU studying applied physics. I have some experience with Linux regarding, or rather through VirtualBox, and for the purpose of DFT course, we've been using Quantum Espresso, and in this semester we've also been working on this cluster, so I have some experience with that.
Hello everyone, my name is Luto. I'm lead engineer from Institute of Organic Chemistry in NASA Ukraine, where I did my PhD. I have a lot of Linux experience. I have a remote execution on computer, but it was single node. It's not the cluster. So that's it.
Okay.
My name is Oleg. I am working here in KAU doing research in material science, and I have a huge experience working with these clusters. And maybe I will learn. I hope I will learn something new. This course.
Oh, okay. I'm junior researcher. I will be for theoretical physics. Main interest in physics. I have some experience with the cluster, writing code in C, mainly C++. Have some knowledge back in 2008 about OpenMP and very basic MPI. That's mainly also CUDA some, but that was also very, very long time ago. That's all.
Okay. Like I said, so yeah, we won't go to CUDA much because we don't have like a GPU cluster available. But yeah, we will cover the basics of working with the cluster, how to log in, how to actually run stuff there. And then I will show, yes, basics of OpenMP, how to write a basic OpenMP program, and how to write a basic MPI program. That's
all the configurations OpenCL or Cycle, they won't be covered.
no.
Okay.
but we can, I mean, that's the plan for the first 3 days, basically. And on the 4th day, we can talk about, like, if you have questions about like some different technologies or like some your own requirements, your own projects, then we can all talk on that on the last day. Yeah.
Okay, I'm Anton, research fellow from the same institute. Therefore, I sometimes use BHP cluster during my research, but I usually use as in built-in parallelization in many statistical packages. I mostly wrote in Python. Also, I'm an Ubuntu user, but I don't know my level as a user. But according to my own experience, I guess that ChatGPT plus Stack Overflow plus Stack Exchange is enough to do mostly everything.
Yes, kind of, yes. I mean, ChatGPT is great. I always use ChatGPT as, let's say, a bachelor student, but who has read a lot. But sometimes when ChatGPT gets stuff wrong, it's good to actually be able to understand what mistake it made and to correct it. But yeah, again, like I said, this is a really workshop about the basics of HPC. So if you already use the cluster for your daily work, maybe you will not find much new stuff in the hands-on sessions. But maybe you will find some interesting stuff in the presentations about the theory. But you'll see. And like I said, for the last day, there's this option to like individually focus on some other interesting parts.
For me, I'm a PhD student in the Institute of Medical Physics, which is also located here. Well, I occasionally use the ATP cluster for the DFT calculations, but I mostly use pre-made scripts written by Oleg. And while I roughly and generally understand what they do, I have never actually wrote one myself from scratch. So I think this will be very useful.
Okay.
Okay, I'll say a few words about myself then as well. My name is Vladimir. I work at Kyiv Academic University as a senior research fellow. Regarding HPC, I had past experience many years ago, and it was not that much. Like I did some OpenMP and CUDA, but yeah, it was I think around 2010 or 2011. So a lot of stuff has changed since then. So this is also interesting for me.
Okay, so if you have any more questions on me, about me, you can ask now.
Was your plasma physics research in any way related to the thermonuclear synthesis and the plasma holding in those tokamak reactors or something like that?
Remotely. So I was actually doing laser plasma physics. So specifically, I was studying interaction of intense laser pulses with solid targets, so like high density plasma, and in those like extremely high energy interactions, you can have some nonlinear effects where you basically have photons scattering on photons in a strong field, and that can lead to electrons scattering on the strong field photons, and that can lead to generation of extremely high energy gamma rays. And if you go to even further intensities, then those gamma rays interacting with the background field can lead to production of electron-positron pairs, which start basically as virtual pairs, but because of the strong field, they get separated so much that they won't annihilate immediately. And like, so this was kind of like very much theoretical work, but the the production of those gamma rays, that's something that's been experimentally observed with those high power lasers. And of course, the idea is to use it instead of like traditional gamma ray generators. And regarding fusion, I never worked on like plasma fusion in tokamaks, but there's this inertial laser fusion idea. And the facility I worked at didn't have lasers suitable for that. We had lasers which had much more intensity, but very short pulses. And so it's a different regime that what you need for laser plasma fusion. Instead, we used it for, or would have been using it, because when I left that institute, the machines, the lasers themselves still weren't functional. There was an institute in Prague called Eli Beamlines. I then moved to Germany, to Dresden, when I worked since 2020. But you could, for example, create something we call warm dense matter, like a state of matter that's expected to be in the center of heavy planets like Jupiter, where the matter is compressed and heated by the gravitational force. If you do this in a lab using lasers, you basically compress a small piece of matter with lasers that also give you this extreme heating and pressure, and then for a split second you can watch how that matter behaves. And of course, then you try to, from that small piece, you try to generalize how it actually behaves inside Jupiter, let's say, how the different radiation that comes from that, like, goes through the other layers of Jupiter, and then guess what you should be seeing if you look at Jupiter. So yeah, but and also there's applications to particle acceleration, like electron acceleration and ion acceleration, due to the effects of like plasma waves that you generate when you hit your target with this extremely strong laser. It's like a smaller problem, because then usually you're looking at something in the vicinity of, let's say, tens of microns. So it's a smaller problem than laser fusion. In laser fusion, your fusion fuel pellet is about 2 millimeters. So from the point of view of the simulations and also like all the effects that are in there, this laser fusion capsule interaction is much more complex than just shooting at, I don't know, like a foil or a gas jet and observing the accelerated particles. So yeah. Okay, so let's move to the presentation about clusters. So what we will be talking about is high performance computing, or like massively parallel computing for scientific purposes, for physical simulations mostly. So I won't be talking about like large clusters for virtual machines on Amazon Web Services, it's specifically for simulations in physics, because that's where I'm coming from. But more generally, like HPC clusters in academic institutions, not the usual usual commercial stuff. So what is it about? It's all about processing data or generating data on a large number of processors. Yes, processor is the one you have in your laptop, but many of them. There are different in physics, I would say, like the two main options how to use a large number of processors is either so-called grid computing, that's very often used in high energy physics at CERN, for example. There you have distributed nodes, so very often the grid is not something located in one building, but as CERN, for example, the calculations can be distributed along the world in different computing centers, or some of you might know some projects that you can even, like distributed projects that you can run, where you can run your own node at home. There's this folding at home, for example, project which solves the issue of folding proteins, or this famous, I don't know if it's still on, but the first one I think which used this was the SETI, SETI at home for analyzing signals from distant stars and looking for evidences of extraterrestrial life. Unfortunately, we didn't find any. So and that was a very old project. I'm not sure if they're still operating, but the way this works was you have a large computational problem, which you can divide into very small pieces, which you then distribute to those low power nodes on the level of a desktop or a laptop computer, and then distribute it through internet, basically. Nowadays, that's the only network used for that, and then each of the nodes make the calculation and send the results back to some central server that then is doing some specific analysis. We will not be talking about this approach. We will be talking about a different approach, and that's computing on clusters. A cluster is a large computer made of many nodes, where each node is basically a single server with its own CPU, with its own memory. And usually, most of the time, actually, I'm not even sure if, I mean, I would have said always, but maybe there are some corner cases. So let's say usually a cluster is located in one data center. It's a big computer in several rooms of a single building. They use fast interconnections. That's again the difference to the grid, where with the grid you can just transfer data over internet, over slow connections, because you download your piece of data. It doesn't matter that much how long it takes you to download it, and then you upload it when you're done or when you're back online. In the cluster, you use fast connections like 10 gigabit Ethernet or 100 gigabit Ethernet, or specialized protocols and even specialized hardware like InfiniBand is probably the most common, most famous, or like really custom-made hardware. This Korean K computer use something they call Tofu interconnect, and those connections are like much faster than internet or even your regular Ethernet, because very often you are basically just supplementing the super fast access to your local memory because your task is distributed among the nodes, and sometimes you need to communicate some information between those nodes. And mostly the clusters are homogeneous. That means that all the compute nodes are the same type, exactly the same hardware or very similar hardware. Heterogeneous clusters also exist, but it's much more difficult to utilize them efficiently. So unless otherwise specified, I will be talking about homogeneous nodes. And oh, sorry, this is a bit of older information here. But in general, a cluster comprises of many nodes. Like I said, each node is basically a single server, and you can have like tens of thousands of nodes. And of course, nowadays, we have many core CPUs with AMD leading with 128 core CPUs. So each of those nodes will have one or more of those CPUs. Very common configuration is 2 CPUs per node, for example. That gives you 256 cores per node in the case of AMD. So sorry for that. This is I didn't update the presentation. This was some Chinese cluster, which was the biggest at the time I made this slide. But today, if you're interested in seeing what are the actual biggest clusters in the world right now, there's this website top500.org, which shows you.
Not on the screen now.
Oh, sorry. This is the top 500 website, and it's a list which is updated twice a year and shows the largest clusters in the world. So as of now, Frontier US cluster is still the biggest one. You can click on the details and you'll see that Frontier is based on AMD EPICs. Has a total of 8.5 million cores. Uses its own proprietary interconnect, so it's not on InfiniBand, and it's been at the top already for 3 years. The power of the cluster or like its speed, its computational power is usually specified in flops or floating point operations per second. This is some theoretical value. Or this is a theoretical value. This is a value. A petaflop is oh my god, 10 to the 12. Oh, and exa is 10 to the 15. 15 is peta. Okay, so 10 to the 15. Tera is 12. Yeah, right. So 10 to the 15 floating point operations per second. This is a theoretical maximum calculated from what the chips themselves are able to do. This is a measurement of some typical performance measurements with LinPack, which does some linear algebra operations. But again, your custom software will very likely never reach this value, because even though this is a measurement of some actual running problem, it's kind of like a synthetic performance number, because you will very likely never be just doing huge matrix multiplications, but also your algorithm will comprise of some other steps which will not have this ideal performance.
Another interesting field is power consumption. The
Yes, of course.
Gigawatts.
Yes. our our consumption is can get really huge. But yes, you have 8 million cores. It's it's in yeah. I mean, but still, you have 22 megawatts. Like you can basically build a small power station just to power your cluster.
Facility which requires its own power.
Yeah.
Power system.
And there's which also reminded me that there's another similar list called Green 500 and Green 500. Oh, now it's a part of the top 500 website. So that's a new thing. And Green 500 takes into account also energy efficiency. So watts per gigaflops per watt. You see a Frontier or a part of Frontier. This is not the full Frontier cluster. Also has a is kind of pretty energy efficient. But yes, those things consume a lot of power, but very often it's still much less than some experimental device. So if you take for example, those laser plasma fusion experiments, then it's still much cheaper to do several thousand simulations than to do one actual experiment. So yes, in order to utilize those big numbers of cores, big numbers of nodes, you need to have also efficient and well scalable algorithms. Scalability basically means how well your algorithm performs when run on multiple nodes compared to a single node. I will talk about that later. What is an algorithm, or like how I will use the word algorithm here, just in a very, very general sense, it's just a sequence of operations. And in our more specific case, computer simulations in physics or natural sciences in general, we will be manipulating numbers in computer's memory. What most of us know, because I suppose all of us has some basics of programming, what we do are sequential algorithms. So operations are performed one after another, kind of like cooking. But what we'll look into is parallel algorithms when some operations can be performed at the same time as others, like cooking in a big kitchen with many cooks. As I said, we are manipulating numbers in memory of the computer, and those numbers are some abstract representations of some real world objects, elements, or something. And specifically in physics, we manipulate scalars, vectors, matrices, scalar fields, vector fields, tensor fields. And in a computer, we can represent scalar as like a single number, a single piece of memory, a small piece of memory. A vector can be defined as a starting place in the computer's memory and the length of how many elements from that starting point I can take, or as several places in memory. The vector doesn't necessarily need to be stored as a continuous piece of memory. In computer, the numbers are of course stored as binary, zeros and ones. I also need to choose a representation of those zeros and ones, how to convert them to some number or like floating point number or double precision number that has to be somehow prescribed. And those ideas, those of you, oh, I forgot to ask your experience with C or C++. Is there someone who never worked with C? Oh,
Only Python.
only Python. Okay. So for the non-C people here, I mean, oh, Python. So in C, variables have types. Okay, you know that. That's good. And so this uh, so if I define my variable to just be a float or just a double, I'm defining a single number, and this is telling me I'm creating an array of doubles, and specifically this is a two-dimensional array. So it's an array of arrays of doubles. In C++, you read the type from right to left. If it's defined like this, this is some C++ thing. It's a templated generic list of doubles. And this would define a so-called vector. Vector is kind of like an analog to array in C++, let's say. And so this would be, again, a two-dimensional object, a vector of vectors of doubles, basically a C++ kind of equivalent to the C two-dimensional double array. In computer, of course, we have also pointers that are variables that that point to some memory variables that hold memory addresses. So they point to some different places in the computer's memory. I don't think that has any like sensible analog in the real world. But for most of these others, if you have, for example, this list or a vector of numbers that can represent a scalar field. So, for example, this can be a two-dimensional field of scalars, or you can have like a 3D vector of doubles here. Then this vector here is not like a physical vector, but it's different way to say array in C++. So we can have array of 3D vectors, then that would represent a vector, a one-dimensional vector field of 3D vectors. Okay, so that's our general problem, to write algorithms that manipulate these things in computer's memory in order to represent these ideas in the physical world. For that, we use computers, and they use big computers. So this is a picture of the Summit computer from 2018. Back then it was, I'm not sure it was the first one or the second biggest in the world. And this Frontier computer we've looked at on the top 500 list is basically the continuation of this United States effort to stay on the top, because we've seen that Frontier is on the top since 2021. And this first part of presentation I first made, I think, in 2019. And there was this Chinese computer for many years at the first place until it was displaced by Frontier. So this is Summit from 2018. Frontier probably looks somehow similar. And this is the biggest computer from 1951, the EDVAC computer. EDVAC because it used vacuum tubes to store as the computer memory. Now we of course use transistor chips. And this question here, what do these two have in common?
The size.
The size, yes. They were the biggest at their age.
Of course. Price.
Price, yes, very likely in general.
It was located in the United States.
Yeah, that's also true, but
Power consumption.
I think EDVAC had much less power consumption. Like really, the stuff we're doing nowadays. I mean, yeah, it didn't consume that much, and wasn't that efficient. Like what we do nowadays is much bigger with much higher absolute numbers of power consumption, but also like in all the relative indicators. One thing they also have in common with my laptop or my phone.
Like they include some parts of the so-called von Neumann architecture.
Exactly. The architecture of those computers, the basic idea of how you connect, because I said the algorithm is manipulating numbers in memory. So for that you need memory, and for that you need something that manipulates the numbers. And there were in the 50s, after the Second World War, there were several ideas of how to implement these things, like how to make hardware that does those things. What won in the end was this so-called von Neumann architecture, which was used for this EDVAC computer in the 50s. And von Neumann architecture is what's used in all computers you will ever see nowadays. I mean, again, all, maybe there are some experimental architectures which are not von Neumann, but the absolute yeah, most of them are von Neumann. What is von Neumann architecture? It's again kind of like a abstract idea of how to make a computer. So you have a memory and you have data, that's the numbers, and instructions. Instructions are the elements of your algorithm expressed in the language that the computer processor understands. So instructions, really like instructions. What should I do? How do I cook my meal? That's an algorithm. How do I simulate the origin of the universe? That's also an algorithm, which needs instructions and data. So both reside in memory. And in order to transfer the data or the instructions between the memory, the storage, and the active part, the CPU, it passes through some bus. Well, bus is literally a series of wires and maybe some chips that help this process of transferring data between the CPU and the memory. And when the CPU grabs the instructions from the memory, it will execute those instructions to operate on the data, which it also gets through the bus from the memory. The instructions are executed in cycles. So the CPU starts the cycle, fetches the instruction, fetches the data that belongs to the instruction, completes the cycle, gives output, maybe writes that output to the memory, and starts a new cycle. And that cycling is driven by a clock. So there is some
Oscillators.
Yes, oscillators. I mean, yeah. No, obvod, česky. A circuit. Yes. Some computer circuit that gives you a clock, which in modern computers, the clock can be variable, but still the timing of those cycles is always driven by some clock. So if you want to calculate faster, what what would be the first idea? Increase the clock speed. Yeah, and the faster the clock speed, the faster my calculation if everything else stays the same. And when you do like more elaborate and faster processes, you also increase the number of transistors on your processor die. And there is there's a law called Moore's law, which says that the number of transistors doubles every 18 months. And you can see here that's Moore formulated it in back in I don't know when, I think in the 90s, but okay, that's not sure. But if you plot the number of transistors from the 70s till nowadays, yes, the number really still doubles every 18 months, more or less. But what you see is that the performance, and there's this frequency wall. At some point, we're not increasing the frequency, the speed of the clock. Yet still, we have like more and more powerful computers. And you see, the way we did it was that at the time when the frequency kind of stopped increasing, what started increasing was the number of logical cores. So that's where we entered the multi-core era of computing. And like I said, nowadays, except for like microcontrollers and some very specific stuff, almost everything is multi-core now.
So before 2005, almost all processors was one core, single core.
Yes, yeah. I
Yeah.
think the oldest computer I have at home was from 2008. It was a Pentium 4. Pentium 4, if I'm not mistaken.
Pentium 4 has one core. Yeah.
And it's a single core.
It was around 2004.
4, 5, yeah. Yeah, it was introduced in 2000 and discontinued in 2007. So the one I have at home, I think, is like from 2005 or something. It still works. It runs Linux, and I have converted it to like a gaming machine. But but otherwise, it's like for serious works, it's absolutely useless because it's also consumes something like 150 watts of power. And
where was introduced spark or power much earlier.
that's true. Yes. Yeah. Spark processors had multi-core processors already in the 90s, and
Or divided 4, and the simultaneous multithreading by 4 or 8 even threads per core.
yeah.
So,
Yes, and that's correct. That was the Spark architecture, and there was also this power architecture. It was also used in some early, I don't know, was it Xbox consoles or PlayStation? Early Apples had power chips, and I know that one of those it was actually called Power 9 because it had
Very proprietary, like very specific, with 13 cores or something. Like it was very, it was 6 cores. It was very good for the time.
Yeah.
It had like
and power is still being produced. So some of the supercomputers still use it.
and newer ones, I think they still release new ones.
Yeah.
Just specifically for super.
Yeah, so I mean, I would say this graph is not really saying that we didn't have any multi-core processors in the 90s. It's probably just that they really weren't that common, or like maybe just like didn't really move those numbers here that much. this is the part where, or maybe it's just about the Intel-based architectures. They yes, but why is this why we stopped increasing the frequency at some point? Why we didn't go higher? The reason is that the frequency, the power consumption basically increases with the third power of frequency. And with the power consumption, you also increase the generation of heat. So it's not just that you would need a lot of power to run your CPU, you would also need a lot of power to cool it down. So in order to go through this around 4 gigahertz wall, if we wanted to do more work in given time, we have to do it in parallel. And yes, we need to deal with systems that do a lot of concurrent calculations, because we need to break that wall by several orders of magnitude. And nowadays, this is nothing that not fancy, but yes, the GPUs, graphic processor units, were using this for years, basically since the earliest GPU accelerators back in the 90s. Those were specialized chips that were doing operations in parallel, that they took some data and executed the same instruction at the same time over a large array of data. That brings me to the next slide, actually.
How do you think, for what time this computer you showed, 2018 computer on the photo, for what time it remains actual? So since 2018, it was like 6 years, and the number of processors increased like 6 times.
But these clusters, they usually keep getting updated and upgraded.
Oh, just one thing about this slide. This is not telling you the number of transistors in the whole supercomputer. This is about the number of transistors in a single chip.
Yeah, I think that the chips inside the supercomputer, they are not modern.
Yeah, no. In that one they are, but I mean, the top computers here in top 500. If you look at the list, you will still find summits somewhere near the top. Like this really takes years to build, years to prepare, and it's really like a kind of like a strategic issue on the level of the whole country. It's like a competition between the US, China, and like Japan and Korea.
China likes all
and Europe, the whole Europe. Yeah. So now you have Frontier at the top. That's from the US. Aurora is from US. Oh, I had no idea Microsoft came in with their own thing here. Now the Japan has this Fugaku computer based on the RISC. I think that this is based on the RISC-V architecture, or is it? They have this Tofu interconnect, and I think that this is actually. Oh, it's ARM. Sorry. Yeah. ARM. No. We still don't have RISC clusters. That's. Or do we?
Yeah. When do you call them supercomputers, and when they're just clusters?
Oh, cluster, I would say, is a supercomputer.
Clusters.
Okay, it depends. So I would say you call it a cluster when doing a lecture. You call it you call it a supercomputer when applying for a grant. Here's Epic. And Summit is still yes. Seneca has a big one. Finland, and Summit is still on the 7th place. And it was the first 6 years ago. Yeah. Oh, and where's the Chinese camp? Maybe they decommissioned it or something, or like if. Okay. No idea. I think Chinese are not in the top 10 anymore. And you see, of course, like most of them are in the US. Those European clusters are all pretty new. And yeah, this Fugaku thing, that's like very very cool stuff from Japan, because it was when they got near the top of top 500. It was after many years where the top 500 were all dominated by Intel architectures, and this was like the first. That's why I thought it was a risk one, but it's ARM, which is still similar to Intel architectures, but it's not an Intel architecture. So that was kind of a big thing back then. Yeah, here. So
it's not on the screen.
Oh, that means
I guess you need to minimize.
Sorry. No, let's go back. Yeah, here. So again, a very general idea, something called Flint's taxonomy, and that's a classification of parallel architectures based on the instruction part, that's like doing something, and the data part, that's like manipulating the numbers. So the oldest one, single instruction, single data, that's sequential processing. At the same time, I take one piece of data, I take one number, and run a single instruction on that number. Then there is something called SIMD, single instruction, multiple data. And that means I have a single program, single set of instructions, but instead of applying that on one number at the same time, I take several numbers, a bunch of numbers, and at the same time, by the same process, at the same time, run those same instructions on all of these numbers, and again, store this result as some other array of numbers. That's how GPUs operate, but that's also all of the nowadays processors have some so-called vector instructions. That's those SIMD instructions. That's they call it something like SSE, AVX, and like many other. I mean SSE and AVX in the Intel world, and some other fancy names for ARM, ARM, or those Spark machines, for example, etc. Then there's this multiple instructions, single data thing that we will not really talk about. So you have the same data, but you run different instructions on that same data. That's usually used in redundant systems. For example, navigation systems for autonomous, I don't know, rockets, where you need to make sure I mean, rockets with people, for example, where you need to make sure that the people in the rocket don't die because of some navigation error. And one way to ensure this is that you will have different implementations of the navigation algorithm, even maybe run on like different type of hardware. You feed it the same input and you expect the same output. And you can, for example, have, I don't know, 3 of them. And if 2 agree, you accept the result. Or like for some really mission critical system, you might require all of them to agree on the same result. If they don't, there is some error, there's some issue with one of those subsystems. So yeah, not really that common. And in the end, there's this multiple instruction, multiple data, and that's basically distributed systems, either really distributed system as in different nodes run a different instance of a program, so they are executing different instructions at the same time, and each of them has their piece of memory, so they are also operating on different data, or in multi-threaded setting, each thread is at a different part of execution of maybe the same algorithm, but they're not executing the same instruction at the same time, because one's maybe fetching from the memory, one's doing some addition, one came across some if condition and is executing something else than the different one. And they also operate on different parts of memory. They're not reading from the same part of memory, but each fetched a different number from a different part. So we will be mostly talking about this multiple instruction, multiple data case in this workshop. So all of that has the one reason, and that is we have some problem we want to calculate, and we want to calculate it faster, or we want to calculate a bigger problem, but in some given amount of time. So all of that, including that top 500 list, is about performance. And there's something I found somewhere, completely forgot where, but someone called it the 7 dimensions of performance. So what all you need to take into account when talking about performance on a cluster. So you have computing nodes. That's the one computing node itself. Those are somehow interconnected. So that's like on the highest level, it's communication between the nodes. That's something usually very slow. Like sometimes you can also hit the limits of the speed of light, actually. Like if you were on a grid and your nodes would be distributed like somewhere far away. But even in the smaller setting, because you're really talking about nanosecond differences with those fast clock speeds. So even in a cluster, the distance between the nodes might matter. Then the next level would be CPU sockets. That's when your node has multiple CPUs. Then each of the chips has its own bus and has to communicate through that bus with the memory or with the other CPU. So like literally on the motherboard, you have those two chips, and how they connect to the memory and how they communicate with the memory. That's on this dimension. Then you go inside your CPU, and you have this dimension of cores, the number of cores in your single CPU, and the topology of so-called package. Package is basically the chip itself. So how the individual circuits are laid out on the chip package. Then there's something, the hardware threads. That's in the Intel architectures. This is basically the same as cores nowadays, but you can have a single core that also has several a single core that can run multiple threads at the same time. hyperthreading is something that's like somewhere in between, that on Intel architectures, with hyperthreading, your core can run 2 threads at once. It's not like full threads because those threads cannot execute the same type of instruction at the same time. Then ports, that's again something implemented in the chip, and this is something that allows you to, and that is okay. Ports and pipelining, I'll explain at the same time, because it's like maybe too detailed distinction, but your instructions typically are like fetch something from memory, fetch something else from memory, do some operation like addition, take that result of the operation, put it back to memory. And instruction level parallelism and kind of superscalar parallelism here means that if I'm fetching like a different circuit is fetching the memory than the circuit that is doing the addition. So what I can do is, if I know that after my addition, another instruction will first start with fetching the memory, I can, while doing the addition, I can already start fetching the memory for the next instruction. So in that case, if those instructions are not the same, but like kind of like a different type at the same time, I can do them in parallel. And almost all existing chips do that. And finally, vectors. And so memory has also many layers. I will show that later. But vector would be the lowest layer inside your chip. When you fetch something from the computer memory to the chip, it also needs to be stored somewhere. So the chip has so-called registers, which are pieces which can like hold a single number in all the chips. And in newer chips, vector of numbers. That's those SSE instructions and AVX instructions. They also have corresponding registers which can hold multiple numbers at the same time. So if you want to write a well-performing code, you kind of need to take care of all of that, except the hardware stuff. So let's say you don't need to consider pipelining ports and hardware threads, except like whether you use them at all or not. But you need to think about the efficiency of usage of your vectors. That's like the lowest level. Efficiency of multi-core parallelism, efficiency of your socket parallelism. That's important about like how you fetch your memory. If your memory access is linear, or if you need to randomly skip to different places in memory, and then efficiency on the level of computing nodes. That's how your individual nodes communicate with each other. So a typical cluster, again, let's go from the highest level. Typical cluster looks something like this. So this is not part of the cluster. This is my laptop. This is how I connect to the cluster. I connect to the cluster through some login node, which just like, yeah, allows me to log in and operate the cluster. Then I can have, then the cluster does the work on the compute nodes. Those can be the same type, or in a partially heterogeneous cluster, you can have different types of nodes. For example, some have GPUs or some other accelerators, or like some nodes have large amounts of memory per node. And yeah, most of the nodes will just be whatever is the most common use case for the cluster. And then this connects to very often distributed storage systems. So the nodes themselves have some local storage, but very often you go to the big data is stored somewhere else on some specialized storage nodes. On the lower level, you go to a CPU. Nowadays, CPUs also have integrated GPUs. They are not used for computation, but this is like some typical Core 5, Core 2, yeah, i5 architecture or something like that. 4-core processor. Those are the cores. Cache is again some level of memory. I will talk about that later. Memory controller is what connects, like literally with wires, to the RAM, to the memory. This is a part which basically operates the hub, the bus. So the bus would be the wires here themselves, but this takes care of the communication between the memory and scheduling of the cores, distribution of workload along the cores. So the data comes through the memory to the cache, and then the cores read it here from the cache, do something with it, put it back to the cache, and the memory controller puts that back into the shared computer memory. Again, this is just this general idea. You have this processor, and here you have the bus. On the bus, you have some controlling chipset. In some architectures, I think actually most architectures, this is not really a separate chip, but it's been made part of the processor itself because it's faster then. And then on this bus, you have all the different peripherals. Okay, no. So here the memory is already going directly to the CPU. This is the chipset for like the slower peripherals like PCI Express, audio, hard drives, USB ports, and everything like that goes through some other hub. And so that's a typical CPU, multi-core CPU. A typical GPU looks something like this. So here I have the CPU and the bridge and the hub and the bus PCI in PCI Express nowadays. And that connects to the so-called host interface, which is communicating between the GPU itself and the CPU. And the GPU is made of many vertex and shader processing units. Those are very primitive chips. You've seen that here. A lot is spent like on this cache, and even in here, like a lot of transistors are actually operating some out of order instruction caching and even branch prediction. So the CPU tries to do some calculations in advance, because then if it correctly guessed what will be the branch you've taken, you can save a lot of time by actually having that result ready. This is not being done in GPUs, and there's like, especially not branch prediction. GPUs count on having a lot of those individual processing units. In big GPUs, it's in thousands of units compared to the like hundreds of cores in the best CPUs we have. And they are much more primitive. They provide just those basic arithmetic and memory operations, but by this sheer number of them, they can reach high speeds if your algorithm supports that. If those things, so all these run the same instruction in parallel on top of the specific memory that's attached to the GPU itself. Those different calculation processing units are connected together through different interconnection networks. Like I said, those nodes will be either or on fast Ethernet or some InfiniBand or some tofu or some that kind of interconnect. The CPU sockets, if you have multiple CPUs, nowadays, okay, this is again old thing. So nowadays, it's all of them use so-called non-uniform memory access. That means that each CPU is physically connected to some part of your memory. And if CPU1 needs some piece of memory which is physically connected to CPU2, the transfer needs to go through the CPU, through the other CPU. And this same situation on those multi-core systems is also on the level of the CPU cores, where those links are like basically through here, those physical links are actually belonging kind of to each of the core. Like this continues here through physical wires to the memory chips. So again, if this core wants to see something that was connected to this set of wires, it needs to ask this core to give me that give it that information through here. Why am I talking about it? And that's because those different memory pathways have different speed and latency. So what you also need to think about is how your memory is structured, how your data is stored in the computer, where it really physically resides. It's obvious when you have multiple nodes that if my stuff is here and I need to pass it through a network to a node which is in a different rack, that it will be slower than when I'm just reading from the memory of the node itself. But it gets worse, even on the level of a single CPU. So the fastest memory you have is the CPU core registers, usually with the latency of 1 cycle, but you don't have many of those registers. Like this is some AVX architecture, so 16 times 64 bytes. Then you have several levels of cache with like the faster the cache, the less you have it. So this L3 cache, that is still part of the CPU die, that's still on the chip itself. It already has some about, let's say, 40 cycles of latency. So if I need to get something from the cache, if it's not in the register, I have to wait 40 cycles before between I ask for that data and I actually get it. Then if I go to the computer's RAM, which is on the order of gigabytes or terabytes nowadays, maybe, I go to hundreds of cycles of latency. And if I go, even if that stuff didn't fit in the RAM either, and I need to read from disk, I'm even on a fast SSD, which is connected via the PCI lane through this NFMe protocol, I get thousands of cycles of latency. For slower hard drives, it can be millions of cycles. So why the processor could have done executed like million of other instructions is doing nothing because it's waiting for the data to arrive. And then this is a big issue when doing computing with GPUs. And that is, in order to get data to the GPU, it has to pass through a different bus as well. So if you calculate something on the GPU, but then your algorithm needs there is some part which cannot be done on the GPU and must be done on the CPU, you need to copy the data from the GPU to the memory with this like around 10,000 cycles of latency. Then from the memory to the CPU, do stuff on the CPU, put it back to the CPU memory and put it back to the GPU memory. So again, you're getting latency on the order of, let's say, 10,000 to 100,000 of cycles. And then, of course, the slowest part of all is communication to other nodes that goes via some network. So InfiniBand can be pretty fast, but if you're on some slower Ethernet, like, I mean, this number can be like even several orders of magnitude worse than just on the order of 10 millions of cycles. So that's the important thing to remember from this. You always have to know how your data travels to the processing unit from the memory in order to write efficient algorithms. And not even to write them, you should also know how your software works, especially if you're working with something that uses GPU acceleration, or if you're doing machine learning and copying, or like even with, I don't know, TensorFlow or whatever, you need to know whether now I'm running on the GPU or am I like reading data from somewhere else.
Okay, thank you.
Okay. So, up until now, I was talking about the hardware and how hardware considerations affect the performance of your program. Now let's move to the considerations of the algorithm itself. Again, in a very general way, let's say you have an algorithm and you want to make it faster by having it run in parallel. So what you would be looking at is the parallel speed up. So something that tells you if instead of using a single processor, I have some problem of size n. I need to find some definition for that size, but different for each of the problems. And yes, here is like technically the worst case time complexity of the fastest known sequential algorithm. So you take the best algorithm, the best sequential algorithm you know, and give him and use the worst case in which it can operate. And then you take your new algorithm, the parallel algorithm, for the same size of a problem, parallel algorithm for the same size of the problem, run it on P processors, and really measure just the time, and then this parallel time, like the amount of time it actually took the algorithm to finish, or like the worst case of the best serial algorithm over the parallel time is your speed up. So like kind of naturally, it just tells you how much faster I am if I am running on P processors. So except for some specific corner cases where the algorithm could have some branches that can force all the processes to end earlier. For example, if you were searching through a tree and you have a big data structure and you need to find some node in that data structure, then yeah, you can get higher speed up than P, because one of the processors can be just lucky and get it immediately at the start. So even and it can be like processor number 1000. So if you were running on a single processor, it would take days to find. If you were running on 1000 processors, just because randomly the last processor immediately found the correct solution, your algorithm can exit. But let's just say that we know that all the processors always need to do all the work as had to be done by the sequential algorithm. Then of course the best speed up that you can possibly get is the number of processors. So the theoretical best option is if I'm running on 100 processor, if my algorithm is perfectly designed, if it can be even perfectly designed, the speed up can be 100. Yes, and in practice, you will never reach this theoretical value for many reasons, because of course this the real parallel time is not made of just computational spread, but a so-called overhead. That's like anything that wasn't part of the serial algorithm, but you had to add because you are running in parallel. So for example, typically it's communication. So the best speed up we can hope for is P, but can we actually always write an algorithm that will have this, at least theoretically, will have this speed up? The answer is no, because otherwise I wouldn't have been asking, right? And the reason for that is something called Amdahl's law. In HPC, when we talk about the limitations given by the Amdahl's law, we call that strong scaling. So what's Amdahl's law about? I have a problem of a fixed size. So the size of my problem doesn't change. What changes is the number of processors I throw at the problem. So I need to do some simulation on a grid with 1 million cells, and I will try how fast it runs with a single processor, with 10 processors, with 100 processors, and finally, maybe ideally with 1 million processors, it should finish 1 million times faster than on a single processor. Yeah? Ideally, theoretically, very theoretically, and only if the whole algorithm can be parallelized. So what I mean by whole algorithm can be parallelized. In a real algorithm, you always have some sequential part of computation, even if it's just setting up the domain or something like that. So you will never have an algorithm which is completely parallel, like talking about the full algorithm. At some point you will gather the data, for example. If it's just that first you distribute the data, then you run everything perfectly in parallel, and then you gather the data, then it's fine. But sometimes you have parts of algorithm that cannot be parallelized. For example, you need to do some, I don't know, averaging somewhere in the middle. So yeah, typically it's about parts of algorithm where you need the information from the whole domain at the same time. So then when you look at your serial algorithm and say which parts you can parallelize and get those parts which cannot be parallelized and measure the time that it took, measure that on the serial algorithm, then this sequential part of computation that cannot be parallelized or isn't parallelized in your parallel algorithm, we call it F. Parallel part will then be 1 minus F. And then this gives you the maximum speed up on on P processors. So that tells you that even if you, that tells you there's a hard limit, and kind of intuitively that hard limit is my even if my parallel part would completely disappear and be calculated instantly, I'm always left with this sequential part, because that cannot be sped up, that cannot be parallelized, that cannot be done faster. So if and this is a pretty hard requirement actually, because if 90% of my algorithm is parallelized, that means I have 10% of a sequential part that looks, hey, 10%, that's not that much. But that actually means that I always need at least 10% of the total running time. So my maximum speed up in that case is 10. Even if I use 1 million processors, I will only have a 10 times speed up. So yeah, here, like, I mean, if your parallel part is 50, then it's probably not even worth parallelizing it, because maximum speed up you get is 2, theoretically. And if you add some communication overhead and whatever, maybe you'll get something like 1.6. Like, is it really worth it to parallelize that thing? Probably not. But again, like with 55, you have the speed up of 55% parallel, you have the speed up of 20 maximum. So even with thousands of processors, you will never go over 20, in case 95% of your algorithm was parallelized. So when writing your own algorithms, this is something to keep in mind.
But what are some real cases of parallel algorithms? How high does it go? 99%, 99.9?
Over, yeah, 99.9 point something. Like, but no, those algorithms with like, for example, 10%, they also exist.
Yeah.
That just really means that, okay, I cannot really, like, it's not useful for me to go to such large cluster in that case.
Which are being used on like industrial scale.
That's there's another thing. I'll come to that in the next slide. Because the question here was specifically, if I have a problem of fixed size and throw more processors, will I get the result faster? Or how faster I get the result? So if my problem is of this type, then yeah, I really need to aim for like 99.9% parallelization, something like that. That's not always possible. And but what might be possible, so that's the strong scaling case. What might be possible is something different called weak scaling case. And that's just rephrase the question and kind of solve a different problem. So sometimes I can increase the size of my problem while keeping the sequential part constant. Typically, if I do some simulation and the sequential part is that I need to gather the data and I don't know, calculate some average, because I need to get that average from all the parts, and it's just like calculated in one piece, and then use that average in some subsequent part of the algorithm. And if that now the time of time of calculating that average won't depend on the number of on the number of processors for where I get it, or on the number of cells. Can be done. Then I'm talking about a different scaling property, and that's called weak scaling. So weak scaling is telling me, and that's like there's like much more leeway here, because I always have this sequential part, which I cannot do anything with it, but the parallel part can scale much better if the parallel part linearly scales with the size of the problem. Then what I'm doing is I'm adding new nodes, new processing units, not in order to get the same size of the problem faster, but I'm increasing the size of the problem. So instead of calculating for 1,000 cells on 10 processors, I go to calculate million cells on 10,000 processors. And that's a different kind of problem, different kind of scaling. So in practice, a lot of algorithms that have bad strong scaling properties are still worthy of being used in a high performance context if they have good weak scaling properties, because it doesn't allow me to get faster to a solution of a smaller problem, but it allows me to solve much bigger problems on that scale of those tens thousands of nodes or millions of individual CPU cores. Okay. So now I will talk about data parallelism, task parallelism, and those are again algorithmic considerations, but those algorithmic considerations can be somehow mapped to those hardware ideas I've shown previously. So typically, a data parallel task is a task where you have data and you can split that data. For example, you have a matrix and you can there's some operation where you can just operate on submatrices and then at the end glue all the results together. So typically data parallel application. So a same task that's performed by many processing units on a subset of that full data set. And that's typically something that leads to the single instruction multiple data model. So we have single control flow, all of your processing units are executing the same algorithm. They just divide the data pool into parts, and each is responsible for just a subset of the data. Oh yeah, typically this SIMD model. The other is called task parallelism, where you have different tasks which are simultaneously performed by those different processing units, and it can be on the same data set or on different data sets. Of course, you can combine this. So, for example, you divide your domain into parts, and on some part okay, I don't know. You have a simulation with electrons and ions, and use some completely different algorithm to solve the movement of the ions and the movement of the electrons. And some processing units can be given just the electrons, some can be given just the ions. Then each of them is solving a different task. In real simulations, very often you still use this multiple instruction, multiple data model in the way I talked about it earlier. but you are using it on a data parallel system. What I mean by that is, suppose again, for example, for those particle simulations, that makes perfect sense. So you have a domain with many particles, and you solve interactions between those particles and, for example, some pre-described fields. So to each processing unit, you give a subset. So from 1,000,000 particles, you give 1,000 particles to each of the processing units. But technically, so that's data parallel task, data parallel problem. But technically, because they can be some different conditions, some if conditions based on what type of particle I got, or if I don't know, if the particle enters some predefined space, something different should happen to it. So technically, I'm not executing the same instructions on them. I'm executing different instructions at each of the computing nodes. But the problem was data parallel, in that I could parallelize it by splitting the data pool into smaller parts. And while this where all the instructions are the same, this can be executed by those like vector processors or GPUs and stuff like this, where I feed the processor a single type of instruction, and the processor itself has some means to get different types of data at the same time. This model is kind of more complex, because I have somehow like distributed data, and the individual processing units need to decide on themselves what to do with the data, and they decide individually. That's the multiple instruction part in here. And there are those two basic so if I leave out this vector processing part and now focus just on the multiple instruction, multiple data model, there are two basic ways of implementing this multiple instruction, multiple data model. And they differ in the way of how they access the memory. And one is called threading, and the other is message passing. So I'll start with the one which is kind of more difficult to implement, but maybe easier to understand, and that's message passing. So each of my sorry, I always forget. You cannot see the mouse yet. So each of my processing units, each of my processing units is executing some part of algorithm, and in order to get the data, in order to communicate, to coordinate, they send messages to one another. So every process has its own memory space, and because every process has its own memory space, it also means that it can live on a different physical machine. And so in isolation from the others, so I cannot directly from process A see the memory belonging to process A, to process B. If I want to do that, I need to explicitly communicate that I want to see the different piece of memory, and the other processor has to send it to me. So this is the principle of message passing. And that's the way how to parallelize the access to the memory. So I don't own the whole memory as a single processing unit. I don't own, and I cannot directly see the whole memory, but I can somehow ask the other processes to send me their pieces if I need them. And technically, yes, of course, because also since I'm working in isolation, I don't know if the other processing unit is ready to give me the memory. I asked for, because maybe it's still doing some calculation. Then you need some sort of queue where to store those messages, and just like work on them when so the message the processor gets the messages, but it's working on some calculation, stores the messages in a queue, and then when it's free, it will work on them and work on those requests coming from other processors. So that's the message passing idea, which most commonly is implemented using this MPI library, one of the MPI library implementations. And the other way of doing parallel access to your data set is threading. That of course needs hardware support, but as we already said, like most of nowadays has some multi-threading support. And here in the threading case, or so-called shared memory access case, every parallel thread can see all the data. Or yes, of course, I've talked about this NUMA case where it costs you some cycles to get the data if it's physically connected to the other processor on the motherboard. But in general, and from the point of view of the programmer, each of the thread can directly ask to access any of the any piece of memory. So that's why it's called shared memory, because the way if you want to coordinate the threads, if you want them to kind of exchange messages, instead of like explicitly sending messages between one and the other, you just store something in a certain piece of memory, and every thread can immediately read that piece of memory. So in general, yeah, of course, exceptions to that, but in general, on a single machine, threading is faster than message passing, because it doesn't have this message. You don't need to create a message, you need to send a message, etc. You just directly access the memory on the same machine. There are ways to implement this shared memory access pattern on a distributed machine, where you have kind of like a virtual memory space. But then what's really happens behind the scenes is that at some point you need to send the message to the other node. Huh? So then you're like emulating shared memory access on a distributed memory machine. That of course is much slower than direct message passing. And yes, you can create problems with synchronization and memory protection if your two threads decide to write at in the same place at the same time, typically. Still, it is computational equivalent to message passing, in the sense that every algorithm that can be expressed as a message passing algorithm can also be expressed as a threading algorithm. And you can very easily see that instead of so if you want to go, if you have a message passed algorithm and want to convert it to a threaded algorithm, then instead of sending messages, you can just use a designated memory area to hold the contents of the message. And then everything else can stay the same. The other way around, if you have a threaded algorithm and want to convert it to message passed algorithm, then you can just create messages that ask for specific areas of memory. That's this like virtual memory space that spans multiple nodes. I'm not saying it's a good idea to do it like that, but like theoretically it's possible. So on the theoretical level, those approaches are completely equivalent. Yeah. So again, we went from like the higher level message passing to a lower level inside one CPU core threading, where I'm on the motherboard, and the CPU accesses my memory on the motherboard, and then on the lowest level, there's this vector processing, and that's again something that exists in GPUs or the vector instructions in CPUs. So vector, again, an instruction that operates on a set of data instead of on a single number. And those in all existing architectures are expressed as elements packed into a one-dimensional array with like a certain number of elements. Oh, okay. No. It's not really true what I said. Because there's also tensor processing units for neural network accelerators, and those can operate on small 2D arrays, some of them. But in general, most of what you will encounter regularly will be operating on one-dimensional arrays of fixed length. That's the vector instruction, that's the vector register, and the vector registers are being read and written by vector instructions, which perform that single operation on the whole vector at the same time. Similar thing is in those GPU cores, but the GPU core doesn't execute just the GPU core is not, or the stream processor is not just a single instruction, but you give the GPU core a set of instructions, a so-called kernel, which is basically a small piece of program, several instructions, and that whole pipeline is being executed by all of the cores at the same time, again, on some subset of the data they read from the faster GPU memory. As programmers, those are those 3 dimensions that you need to be aware of, and as programmers, those are the 3 that you will probably most of the time ever program. If you will not be doing hardware design or like hardware development, then your algorithm, then you want to think about how to vectorize your algorithms. So look into your algorithm and look if some of the operations can be applied to several numbers at once. Then store your numbers as those vectors and use those vector instructions to operate on those numbers. Very naturally, if your algorithm can be vectorized, then it will also be quite easily threaded, because threading is not vectorization. It's something more powerful, more general, because the threads can each execute different set of instructions, not just a single one. So you can do like if conditions. I mean, you can emulate if condition in a vector instruction by using masking, but in general, it's I mean, it's not really natural thing to write. So threads can execute all those so threads are like full programs, not just those GPU kernels. And yes, if your program is easily vectorized, then can it be also easily threaded. You just like operate on bigger chunks of data than in the small vector instructions. And in the end, when your single node performance is not enough, or if you need to do a bigger problem, you go for message passing, which basically clones in the easiest way how it's usually implemented. You're basically running the whole program, the same executable file on multiple nodes, and those exchange messages over some network. Okay, that's it for the theory part. Any questions to that? Oh. So now the theory will continue tomorrow. But tomorrow you will see how all those kind of like, let's say, abstract concept, but I mean, like on some level they're abstract, on some level they really talking about the physical hardware and the hardware we actually have here at hand, not some idea of a hardware, but limitations coming from historical decisions and the development of the technology around us. So tomorrow I will show kind of like how this is applied. What does it mean for us then to actually write the parallel algorithms? Because as I said, from serial algorithms, you know, many concepts like, for example, those if conditions, branching, or for loops, iteration over a set of data, and all those idioms we know from serial programming have their counterpart in parallel programming, but sometimes it's not like immediately obvious what kind of counterpart it is, and most importantly, some might have some limitations regarding those like race conditions when multiple processing units would like to manipulate the same piece of data at the same time. That leads to some issues that you need to be aware of. So yeah, that's the plan for tomorrow. And for today, we will now try to connect to the cluster and run some basic stuff on the cluster. Before we do that, this is our cluster. Sweet. So you will probably read those things faster than me, but so this is a user interface. So this is the login node. So what you do, if you remember that some random cluster picture I showed at the beginning. So as a user, you log in here to the login node somehow to internet or something. Then the login node is through some switch connected to the compute nodes, and there are 4 different types of compute nodes. Are all those compute nodes? Občisľování has something to do with numbers. Yes. So computing, calculation, yeah.
Computational servers.
Yeah. So yeah, they were added through the years, updated. The cluster was being so this is a typical case of a heterogeneous cluster, but with like, of course, homogeneous subparts. So very often you will not be running your algorithm on one of the E5 nodes and one of those silver nodes here. Yeah, your algorithm will just be run on the, like, if you reserve multiple nodes to run your algorithm, you will always get something that's within one of those homogeneous subsets. So through some hardware, some wiring, it from the login node, you reserve space and time on the some other resources, time and space on the compute nodes, and then there's a central disk node for storage node where you store the probably it also holds your home folders and the bigger pieces of data. Now, of course, this communication is through a network, so it will be slow if you have some algorithm that needs to access some disk data very often, or like write some data, or it's not enough to use this 256 gigabytes of RAM. You need more. Then there is some local storage on each of the nodes, which is faster than it's called scratch storage. It's faster than accessing this main storage, but belongs to the node, so very likely it won't be accessible after you finish your program. Yes, so most of our communication with the cluster will happen on this node. It will always be written through this node, but we will do a lot of stuff on the login node, and then the calculations. But in this case, I would recommend also program compilation, etc., to be done on the compute nodes. The reason is that very specifically on this cluster, the library versions and the compiler versions on the login node are different than that on the compute nodes, and that can lead to problems if you compile your program here and then don't set up the equivalent of your library environment here. Okay, so let's look in the chat. Okay, after the workshop, let's chat about this after the workshop. So now let's log into the cluster. So who is on Windows here? Okay, you have PuTTY installed. Have you ever used SSH before?
I have SSH in terminal.
Okay, okay.
I have or NSCP or another tool,
Yeah.
like there are options.
So everyone else is on Linux. That's great. I'm on Linux here as well. Unfortunately, this computer is on Windows. I haven't used Windows to connect to something through SSH for about a year or more, but yeah.
Shared on this.
Oh, that thing, of course. So let's change to sharing has stopped. It's not what I wanted.
And everyone who still doesn't have accounts for the cluster, who don't have login credentials, message me. I'll send you the login and password.
Yeah. So is there anyone who never used SSH before? But you have okay. So you have installed some SSH client PuTTY, or will you be doing using the? You have PuTTY.
I installed, like they mentioned, something like WinSCP.
WinSCP is for copying files.
You actually have an SSH built in Linux.
And yeah,
You need to have something, some command to enable it. It's I sent it to you. I have some around.
Here we go.
It's like copy paste the commands to enable them.
You know if this will allow us to use this old RSA algorithm?
It should.
Okay.
Basically, as far as I remember, the latest Ubuntu or
Ubuntu doesn't. This
Yeah.
Linux implementation, I think, just doesn't get. Ubuntu, yes, you have to write a config file to rest.
So one thing I'm not sure about, because it didn't work for me from Prague, if I can actually use the host name to connect, or if I... Oh, I don't. Yeah, okay. So,
About Windows CP, I just opened it. There is also like some submenu that names entrance and like a protocol of some of like transferring,
yeah,
name of host, port, username, password.
okay. I mean, install PuTTY. Because no. The thing is that WinSCP is for copying files, but we will need to run commands in the terminal. So for that, PuTTY is better, or use this.
Also has console, but yeah, PuTTY like is easier and is better for
Yeah.
So like the website putty.org, I guess.
Or you can use this Windows SSH host.
Okay, you need to install it first, like scroll file. I accidentally. Okay, so install, like this command.
Okay.
And I think this is the only command that you can.
Okay, I mean, we can try the other options later, like old school, click on download, PuTTY,
Yeah.
installed. I think it even has this portable exe file, so yeah, I think you don't even need the installer and can just like directly run this putty.exe.
So yeah, because there's so many exe files, which one? Oh yeah, so putty.
But it's a small, simple program, so. So let me know when you have it. And the Linux people, someone who never connected to the BitP cluster, or Linux, because there's this issue with the
RC.
yes, with the RSA protocol.
Yep, it's up and running.
Okay, good. So how to easily get there? You input the host name, which is cluster UI dot big P cluster UI, sorry, cluster UI dot big P dot if with the wrong spelling dot UA, like this, and click open. It will tell you that it doesn't know the key. That's because you're connecting to the server for the first time. So you click accept, and then it should ask you for the username. So you enter the username, and then it will ask you for a password. So username in my case Password. And when entering the password, the cursor won't move. That's by design. So
It's just a window. Like cluster
UI, UI.
UI.
Yeah.
Okay.
Still no? Yeah.
It's shift itself. And not to Python. Or you can just shift insert.
What?
Shift insert to copy paste. Because
Yeah, but I cannot
it
copy
doesn't
paste
work.
because it's a different computer.
Or Control Shift V.
Yeah.
But
Yeah, I would have.
because it's not the most pleasant password string.
Oh yeah. So
Okay.
get there?
I got the login. And what about like nothing still like?
Yeah, that's what I said. Yes, if you start writing in the password box, like you won't see that you're actually writing something, but you are. It's like a
Okay.
security measure, so that people don't, even if they see your screen, don't even know how many keys you've pressed. It's a very typical feature of Linux terminal password entry forms. So don't be scared by that. It's just the way it works. Okay. So everyone logged in? Yeah. Yes. Someone not yet logged in? You're logged in?
No, I'm already.
Good.
Yep. Done.
Nice. Okay, so this is okay. I don't know if it's somehow easily possible to make the letters bigger, except for
Probably, yeah, probably easier not just to change the resolution.
Resolution. No, here. So can you okay, let's go.
Checking the settings.
So when was the last time you've used 800 by 600 pixels resolution? Well, at some point it was a fancy one, actually. Uh,
1990s.
right? That was the super VGA SVGA. Because otherwise you just had 640 by 480, like.
In modern terminal app, scaling work perfectly.
With what?
In modern terminal app, scaling work perfectly.
Oh, okay. Yeah, okay. So it's just like I don't know how to do it in Putty, but I'll look for tomorrow. again, like I'm used to my Linux machines where like I do everything like without thinking about it. This is kind of a new experience for me. But not new, but it's been a long time since I did it last time. So anyway, if you're all logged in, you should see this login message that will always be there. Most often, the first thing the login message tells you is when was the last time you logged in and from which IP address. That's like kind of also a security measure so that you can be sure it was actually you who logged in for the last time. And then some welcome message, which can be said by the cluster administrator. And finally, the most important part, the command line. The command line can have some configurable options. This is a very typical one. When first it tells you the name of your user, then the @, and the name of the machine you're working on. Usually just the host name itself, the short host name, so cluster UI. The rest of the domain name is hidden because it's supposed to know which domain are you connected in. And then here is the actual directory which we are in. It shows this tilde sign, and this on Linux is a shorthand for your home directory. Unlike Windows, but like web addresses, directories or folders are not separated by backslashes, but by forward slashes. And so this, and you don't have drive names like CD, etc., but everything just starts at so-called root directory, which you can access just by a single slash and nothing else. So this is a path, a Linux path that tells you that in root directory there should be a directory called TMP, and if you if you need this known hosts files for some reason, we'll talk about it in some later lessons. What's this used for? But this tells you a path to a file or maybe a directory. You cannot really tell what's a directory, what's a file. Here it says file, so it doesn't. But yeah, it's a file actually. So I am in my home directory. Maybe I have some files in the directory as well. How can I tell if I'm just on the in the command line? So to list the files in my current directory, there's ls like list. I can. So I already have some files there. If you don't have any files there, you can create a file. If you just want to create an empty file for whatever reason, there's a command that can do it. It's called touch. So if I touch empty file, for example, like this, then if I do ls, you see that I have a new file called empty file here. ls also has two useful parameters, and parameters to the commands are usually passed using the minus sign, not with the like on Windows you might be used to forward slash parameters. But since on Linux forward slash is the separator of directories, then so most most of the commands also have some help. So if you do ls -h, sorry, and not ls. I mean, it has help. probably minus help, but minus h is exactly something different in for ls, and I cannot hide this thing now. So if you do minus help, the program will tell you some details about how to use it. And here we'll find out that minus h is not a synonym for minus help, but to minus human readable. Why is this one the one you should remember? There's also a minus L, which is for long listening format. And long listening format gives you some more information about the files in your directory. The name of the user that created the file, the date and time when the file was created, and the size of the file. Can it be in bytes? It can be in sectors. You're not really exactly sure what the number here means. That's where you use this H option. You can combine those options as like minus L minus H. This will give you a human readable value for the file size. You can also combine the options by just typing ls minus lh. So you don't need to repeat the space minus if you want to combine more options at the same time. This leads to the exactly same result. If you want to repeat the last command that you've run and maybe modify it a little bit, you can press the up arrow that will recall the last command you've used, and you can modify it like this, delete or add parameters. And if you want to know which directory you are actually in, there's this pwd command, it just shows you the current working directory. And you see I'm at /home/bitpstudent2. In Linux, every user usually gets a home directory inside /home. Yeah. And like I said, okay, here you also see that there's some color coding, and the directories in the ls output are blue. We can check that if we create a new directory. For that, there's mkdir, like make directory. So I make directory hello, and by ls I see my directory hello. And to change directory, that's the same as in Windows, if I remember correctly. That's cd. So cd hello. Now you see that the actual directory here changed to hello. And if I do pwd, this is the full path to my current directory. If I'm somewhere deep in the directory structure and I need to go home, I can either use this shortcut for home, which is this tilde sign. If I know that there's this subdirectory hello under here, and if I'm like completely somewhere else in some, I don't know, completely random directory like here, and I want to go to my home directory and the subdirectory hello here, I can write it like this. So this means home, sorry. This is home/hello. And if I just want to go to my home directory quickly, cd without any parameters at all, just cd will bring me home. So very often you will get lost somewhere, or like on Linux, you do everything from your home directory. So this is the fastest way to get there. Copying and moving files, renaming files as well. So for copying, you have a command cp. And yes, you say copy from where to where. So let's copy the empty file to the hello directory. Now I can either go to hello and see my file here, or if I were in the home directory, I can list what's inside the hello directory as hello. Then what I'm seeing is not the current directory, but what's in the hello directory. Yeah. Now my file is also here because I made a copy. If I want to delete the file, or in Linux, I don't delete it, I remove it. That's why it's rm, remove, and the name of the file. So that's not here. I still have the copy in the hello folder. And if I want to move the file from that hello folder to somewhere else, for example, right here, that's mv, like move. So move hello slash txt. How do I say here? Here is a single dot. So single dot means the current directory. Again, I check, yes, my empty file is here, and the hello directory is empty. Okay. A useful command that gives some useful output is date. Date tells you the current date and time. This is good to know because you can put this command at the beginning of your scripts, and then in the output of your scripts, you see when was the time that the command actually, that your script actually got executed. And another one, host name, tells me the name, the full name of the machine I'm logged in now. So that's a date and host name. Again, for Linux people, the equivalent of copying between your computer and the like CP, but between different computers is by the scp command. So if I cannot show it here. For Windows users, there's this Win SCP where you can like graphically.
Yes, STV.
Maybe SCP is again in the command file subsystem. Okay, let's see, well, Windows subsystem for Linux. So now this host name tells me I'm still on the login node, right? And as I told you, you don't really run calculations and simulations on the login node. That's what the compute nodes are for. Tomorrow, I'll show you how to write scripts that run predefined programs on the login node. But I also said that sometimes it's beneficial to compile your software on the compute nodes instead of on the login nodes. And for that, you might want to run an interactive session, or for many other reasons, you might want to run an interactive session where you get a terminal open on the compute node. That's like, that means you need also to sit in front of your computer to actually do something there. I mean, unless you really need to do that, then usually don't do that, because you still need to ask the scheduling system to allocate some time for you. And you don't know beforehand when that time will be allocated to. Oh, sorry, forgot to talk about the scheduling system a bit. I will talk about it more tomorrow, but the scheduling system is some system running on the cluster that, that is scheduling the individual jobs which are submitted, which are put in the queue, in the job queue by individual users. Because you have many users on the clusters, and of course, most of the time, everyone would just like have to have the whole cluster just for themselves. That's not possible. So there's a system where you put your jobs in a queue, and the system decides which job to run and what time, and tries to in some smart way optimize the utilization of the cluster. Because if you already paid money for the cluster, you wanted to like do calculations most of the time. You don't want like half of the cluster to do nothing and the other half just like do something. So for that, I will talk about it more. I will talk more about it later. What now I will want to show you is just like how to get time to run an interactive session, for example, because you need to compile your program. So we will ask for an interactive session with the default values that would assign us a single node for our interactive session. One thing that it will do by default is that it will expect our session. For each of your jobs, including those interactive sessions, you need always to specify what's the longest time it should run. And after that longest time, if it takes longer, the schedule will just kill your job. It's always a good practice to have this, of course, a little bit more than the expected runtime of your program, but not much more, because the closer you are to the real runtime, the better job can the scheduler do in fitting your job. And of course, if your job is very short, then it might like, and for like, for example, I don't know, a single node, and there's many people using jobs with many nodes. At some point, there's like 5 nodes left, but the second smallest job is for 7 nodes. Then it will just have to wait until other 2 are available. But if you know, and it might know that it will happen in like 30 minutes. So if you ask for 1 hour on a single node, maybe it will not give it to you, because it will know that then it would have like reorganize everything. But if you know that you will just using it for like 5 minutes, which we will do in a while, then it can decide, okay, I have 1 node free for 5 minutes, no problem. So in order to ask for a job allocation, this cluster uses the PBS scheduler. And the PBS scheduler is recognizable by having all of its commands start with queue. So queue sub is queue submit your job to the queue, but we don't have a job specification file. So what we wanted was an interactive job. So that's minus capital I is asking for an interactive job. And I mean, that's enough. It will tell me waiting for job to start, and at some point the job will be ready. Now I'm running the interactive session. You can try it like that. If you'll be lucky, then you'll get the time. If you won't be lucky, maybe the cluster is occupied. So to increase your chances of getting your time, and you can specify the maximum time you want to spend in that interactive session. So yes, that increases your chances of getting in. Just be sure that it's long enough so that you can actually do everything you wanted to do in that session. So for that, that's minus L. And the parameter is called wall time. And the format of this wall time is hours, days, optionally, hours, minutes, seconds. So let's say I will just ask for 1 minute.
Or we will be 1 hour here.
This is 1 minute. And yeah, okay. So I will do something for 1 minute. You yourself can do like 10 minutes or something, because of course I did 1 minute because I want to show you what happens after if I have my my interactive session open for longer than 1 minute. And you can check the first. You already see that you are not on the login node because the node number is written in the header of the command line. But of course, you can also use this hostname command that will tell you that you're on node called A46. You see that you still are in your home directory. So your home directory is accessible from the compute nodes as well as from the login node. You can check the type of the processor, for example. I should have done this at the start. So, okay. This is what happens when I go over the limit. My job gets killed, and if this, since this was an interactive session, I just get kicked out of the session. Weird. I'm still on the node, but maybe. If you want to end the session on by yourself, because you know that you're already finished, you can use exit. You can also use logout. You can also use Control D. Yeah. Now, about files, a lot of information on a Linux system is stored in text files or in objects that behave like text files, so that you can access and read the information from the command line. That's like unlike in Windows when a lot of those information are like you have to click on something to get to that piece of information. So for example, let's check what's the type of the processor, for example, that we have connected. If I want to read what's in a file, I can use the command less. That's a better version of an older command which was called more. And the information about the processor lives in /proc/CPU info. And when you execute this, then you will see the information about what kind of processor it is, what technologies it supports, etc. In the speech of the Linux operating system, the processor is actually not a processor, but a CPU core. So on a many-core processor, on a many-core CPU, this is not the only thing you would see. And to scroll down, you can use, of course, arrows or page up, page down, and you see there's processor 0, processor 1, 2, 3, 4, 5, 6, etc., etc. If I go to the end of that file, I see the latest processor 7. That means I'm having 8, not processors, but eight cores on this node, on the login node. If you want to exit from this simple text file reader, press the Q key. Q gets you back to the terminal. So now I go to the compute node again and do the same as I did before. Of course, I completely forgot. Yeah, okay, good. And I forgot what was the original processor on the login node, but it wasn't the Silver Xeon, right? It was this yeah. E5405. Yeah. So now you see that this is a different CPU. That's hopefully good enough proof that I'm really working on a different node. If I
It's easy to notice that there are much more CPUs.
Yes, much more CPUs, much more CPUs. I'm somewhere at CPU number 43, and I'm still not at the end. At the end is 63, so I'm on a node that has 64 cores.
It actually means that those infographics about CPU was incorrect, because I think the largest one on those was 2 by 16. Maybe it should be some CPUs. 2 by 16 by 2. Maybe
Okay, yeah. Okay. Good point. Good point, actually. Yes, absolutely. So let's go to. So here it tells us that the silver 12 core.
I think the lowest one. The lowest.
Oh, that's the newest one. So 16 core. 2 CPUs, 16 core each. I'm seeing 64. Why? So there's hyperthreading. So if hyperthreading is enabled, then each core can execute 2 threads, but those threads to the operating system, that's completely transparent and like mostly completely transparent. Each of those hyperthreads can execute the same type of instructions as any other. And on that most basic operating system level, like they are all equivalent. And if you had a single core CPU back in the days, then you switch to a multi-core CPU, to that operating system, it was like it could use this single core CPU in mostly the same way as the multi-core CPU, at least from the user point of view. And also, if you had multiple single core CPUs, it was the same as if you would have a single, a single multi-core CPU. So to the operating system, for most of the tasks, those things look exactly the same. If it's the individual CPUs, like single core CPUs, if it's the CPU cores, or if there are like hyper threads that can be run 2 hyper threads per core. So if hyper-threading is enabled, then on a system that has 2 CPUs, 2 physical CPUs with 16 cores each, you will see 64 so-called processors in the process listing list. This is like 2 by 16 is 32 physical cores, and each core can have 2 threads running on it. Again, I can exit the less program with the Q key. And I can end the interactive. Okay. No. Okay. I will exit the session and show you one more. No. Yeah. I thought I should see. Is anyone running an interactive session right now? No. So someone run it, because you should be able to see.
Users.
Yeah. No, it's not you.
That you can see only your own tasks.
Yeah.
No, it's some additional command where you can see all answers.
You know,
It's something like you.
like you know. We suspect that we remember that several years ago, the option to see all other tasks was turned off to avoid the addition of possible conflicts between the users. Like, why do you start?
Yeah. Okay, then I can understand that. We back in my institute, okay, we're not using PBS, we're using Slurm, but that's like just another system which is mostly recognized by having all commands start with S. But we can see who's using what, and then we have big fights in the internal chat about it. That's
It's Q stat, capital Q, and you can see the.
No, that's the okay. I will talk about this tomorrow about the different queue types. But yeah, if the configuration is so that you cannot see what the other users are doing, then what you only can see is what you are doing.
You can see the number of run tests, like for example, here you can see that there are 5 tests running. No, run. Or maybe
Yeah. There's 5 tasks running in the long queue. The long is the default, I think.
Yeah.
So yeah, I can at least see that 5 people are running something. If I okay.